Okay, fine. So accordingly, what is this electrolysis? Just we learn now. Electrolysis, that is the process of breaking a larger compound into small, simpler components, passing a current, flowing a current. So let's write down. The chemical change affected by passing an electric current through an electrolyte is known as electrolysis. So a chemical change. Accordingly, what is the electric energy? What is the energy conversion happening here? Electric energy is converted into chemical energy. A chemical change is what brought out, right? So electric energy is converted into chemical energy. The question asks you, what is the energy conversion? Electric energy into chemical energy. Okay, right. So have you done with this? Yes. So accordingly, during this process, the electrolyte is converted into simpler components. Simpler components. Can you please highlight that? During this process, the electrolyte is converted into simple components. So now, what is electrolyte? There are some words we have to learn. Okay, one by one we will learn. Okay. Now, can someone tell me what is this electrolyte refers to? What is electrolyte? There are two words. Very first, you learn these two words: electrolyte and non-electrolyte. Electrolyte and non-electrolytes. Now, usually we know that, right? Metals can conduct electricity, right? Okay. When we take this marker, I'm passing a current. I'm trying to pass a current across this. Will it be conducting current? No. If I take a copper wire, it will conduct the current, right? So, solids that we are taking, usually there are metals who can conduct electricity, who can conduct the current, right? Likewise, some liquids are there, some solutions are there who can pass this current, who can conduct this current. These liquids or solutions, who can conduct current, it is what we term as electrolytes. What lights are they? Electrolytes. So the solutions or the liquids which can conduct current, which can conduct electricity, it is called an electrolyte. Okay. Is that all the liquids and solutions can conduct electricity? No. Some are there. So some they can't. So who can't conduct electricity? It is a liquid, okay? No solids, no gases. Liquids or solutions which cannot conduct electricity, they are called as non-electrolytes. Okay, so how do we find them? What are the examples? We will learn. So shall I write there first? Go to it, please. Liquids or solutions. Liquids or solutions which conduct electricity are called electrolytes. Electrolytes. Non-electrolytes also we write liquids or solutions. Liquids or solutions which do not conduct electricity, are called non-electrolytes. Are called non-electrolytes. Are called non-electrolytes. Okay. Fine. Okay, now is it all the liquids can conduct electricity? No. Some liquids are there. How do you find them? There are some liquids, guys. They got some mobile ions. What ions? Mobile. Mobile ions means moving ions. Freely moving ions are there. Positive, negative ions are there that can freely move within the liquid. Okay. So the liquids or the solutions which got these mobile ions, freely moving ions, they can conduct electricity. The liquids and the solutions which do not have these mobile ions, they got no mobile ions. They have no mobile ions. So they can't conduct electricity. So can you tell me now, who can conduct electricity? Who are having mobile ions, freely moving ions, freely moving ions. It may be electrons also, mobile electrons also, because electrons are also negative charge, right? So simply mobile ions, freely moving ions, if it is present, they can conduct electricity, and they are called electrolytes. They are called electrolytes. So who cannot conduct electricity because they don't have mobile ions. They have no free ions, freely moving ions. So they can't conduct electricity. They are called non-electrolytes. They are called non-electrolytes. Did you understand that? Okay, right. Now, okay, fine. Why they can conduct, why they can't conduct, fine. Who are they? Who are they? Ionic compounds are there. There are ionic compounds. Only by word we understand now, because we don't want to go deep down there. It is a great thing actually. So we learn only the word, okay? Ionic compounds. There are two types of compounds, guys. One is ionic compounds, the other one is covalent compounds. Repeat the word, what are the two? Ionic compounds, covalent compounds. Ionic compounds, covalent compounds. Ionic compounds in liquid state you take, or solution state you take, they can conduct electricity. They can conduct electricity because ionic compounds in liquid or solution state, they got freely moving ions, so they can conduct electricity. Covalent compounds you take the liquid or solution state, they have no mobile ions strictly, so they can't conduct electricity, so they are the non-electrolytes. They are the non-electrolytes. Is that clear? Okay, so that is what given in the first page of that chapter. First page in that particular chapter, electrolysis. Okay, so can you please read that particular part here? How do electrolytes conduct electricity? Quickly read and see. What we discussed now is not given there. Quickly read, quickly read. What do you do? The passage given below that electrolytes part. Quickly read that. Okay. We'll make a small note. Go to your writing book. Go to the writing book. Oh, wait. Check out the page number 5 here. You got a small space on your tube. There we go. Okay. What is it? Now, so we are going to compare electrolytes plus non-electrolytes. What are they? Electrolytes, they are the liquids or solutions which can conduct electricity, which can conduct current. So here, the liquids or solutions. So we don't take any metals. We don't, solid state metals, we don't take. Liquids or solutions which cannot conduct electricity. Which cannot conduct electricity, they are called non-electrolytes. Non-electrolytes. That's the first point. Okay. And why they can conduct electricity? They have mobile ions. That means free moving ions. They have freely moving ions. But here, no mobile ions. So that they can't conduct electricity. No mobile ions. And who are the examples here? Who are the examples? Molten or fused ion compounds. Or else aqueous solutions of ionic compounds and acids as well as bases. Acids and bases. So these people can conduct electricity. These people can conduct electricity. Okay. And here what the example is, you take distilled water. Now distilled water is not drinking water. Okay. Kerosene oil, right? Now here when you take salt solution, here you can take it as like covalent compounds. So let me write that covalent compounds first, and then we take next examples. Covalent compounds, liquids and solutions of covalent compounds. Acids, bases, and salt also you can take salts. Acids, bases, and salts. Examples means actually the types, okay? Types. Okay. Molten or fused means a solid you heat. When you are going to heat solid, it will be melting like it will be melting into liquid. So this is called the molten condition. So what is called molten condition? You take a solid substance. This solid substance you heat. When you heat the solid substance, it will be melting into liquid state. So this melting into liquid state is called und molten. Molten. It's melting, molten, or else fused also is fused also is. Okay. So now tell me what is this molten? A solid upon heating, it's can convert into molten. It's a liquid. It's liquid. It's in the melting state. Okay. And aqueous means same solid. You don't heat, but you're going to apply it in water. It dissolves, let's say. It is dissolving in water. Now what is the solution made? Aqueous solution. Aqueous solution. Example, you take salt, sodium chloride. What is the salt we are using? Sodium chloride. So this sodium chloride crystal you are going to heat. When you heat sodium chloride, solid sodium chloride melts into liquid sodium chloride. That is molten. That is molten. Now, same sodium chloride you are going to put in water. It dissolves in water. It will be dissolving in water. So now what is that? It is the aqueous solution. It is the aqueous solution. You understand that? You heat, it is melting into liquid, that is fusion. Melting, molten state. You put it in water, it dissolves. What is the solution made? Aqueous solution. Aqueous solution. So in this way, any of these components are taken, they can conduct electricity. They are electrolytes. Same way fused or aqueous would take for covalent compounds. Still, they have no mobile ions, so they can't conduct electricity. They can't conduct electricity, so they are non-electrolytes. They are non-electrolytes. You understand that point? Okay, fine. So we'll move into the next part. You can see that there's a small activity given. Can you please read that activity? Quickly read. In that activity, there are some components given. What are the components given here? A beaker, two carbon rods, ammeter, two dry cells, connecting wires, kerosene, salt solution, acidified water, copper sulfate solution, distilled water. Okay. On your tube, here there's a space, right there. Solutions used. Solutions used. It is a part of the setup. Okay. Solutions used. Solutions used. Previous page. Previous page. Yeah, below that activity. Even before that, you have to go in order. Even before that. Previous page. Yesterday there was page. Yeah. At the latter part. There. Yes. Yeah. Solutions used. Right? Only these solutions. What are the solutions? Kerosene, salt solution, acidified water, copper sulfate solution, distilled water. Quickly write only the solutions, okay? Okay. Now we see what do we have? This activity. We have a liquid container. Okay? In that liquid container, out of these 5 liquids or solutions, one by one, I'm going to apply. Okay. And I have already dipped with 2 carbon rods. How many carbon rods are there? 2 carbon rods. Actually, carbon rods means graphite rods we are using. What is the carbon we are using here? Graphite. Remember that? Graphite. Because graphite can conduct electricity. Something like a pencil rod. It is graphite. Okay. So, the other end I am connecting with a wire. Here I have the dry cells connected. You can see dry cells are connected. Longer terminal is plus, shorter terminal is minus. Remember that. Longer terminal is positive, shorter terminal is negative. So how many dry cells are there here? 2 dry cells are there because usually this is the dry cell symbol. Now how many symbols are there? 2 of them are connected. And remember, minus plus should be connected. So you can say this is minus, this is plus. Minus plus connected. Okay. When the dry cells we are connecting, plus to minus, they should connect. Okay. Or else minus to plus, they should connect. Now, here you have an ammeter. What does ammeter do? What does ammeter do? It measures the current. It measures the current and it shows the direction of the current. Ammeter, there is a small needle. This needle measures how much current is passing and it deflects to the direction of the current flowing. Alright. Now, this is usual when we are connecting a setup with the current. We have to connect both the ends, right? Both the ends we have to connect. The wire should be connected both the ends. Now I have this graphite, okay? Only one end it is connected. Can you see only one end it is connected? Can you see that? Other end it is not connected, right? Okay. Now forget about the container. You just take this graphite rod over there here. Okay, the graphite rod is there. It is out of the beaker. When we connect like this, you can see there is no change in the ammeter. Mahdi, listen here. No change in the ammeter. Ammeter will not deflect. There is no current passing. But the same setup, what you do now, you are going to put it inside, you are going to dip it inside a solution. And what is the solution you are going to make here? Let's say you are going to apply kerosene oil. You are going to apply kerosene oil. Bumitil, lama, no? Kerosene oil, you are going to apply. Okay, lama means. No, when you apply the kerosene oil here, nothing happens. Nothing happens. And you apply distilled water, nothing happens. Nothing happens means ammeter will not deflect. Okay. So when there a deflection, no deflection, no deflection. Okay. And then what do? You are going to apply salt solution. You are going to apply salt solution. So when you apply the salt solution, you can see the needle is there. The needle deflects. Deflecting moves. It moves and shows the amount of current it passes. Again you do, again it shows. That means what is passing now? There is a current passing. There is a current passing through where? In this way. It is connected. Connected by, is it a wire? Is it connected by a wire? No. Can you see any wires there? No. Then what is it connected with? By the liquid. Liquid passes the current. Liquid, usually the current passes from the positive terminal to the negative terminal, right? Positive the current passes. Now the current passing here should be taken from 1 to 2. Let's say 1 or else A, B. From A to B, current should be passing. Who is carrying this current? The ions. Can you remember earlier we told you mobile ions are there? Mobile ions, the free moving ions are taking the current from A to B. Free moving ions take the current from A to B. And who have these free moving ions? Salt solution has. Salt solution falls under electrolytes. So when you apply salt solution, there is a current pass. And again you apply copper sulfate solution, CuSO4 solution. You can see there is a current passing. Ammeter deflects, current passes. And again you apply acidified water or else acidulated water. Acidulated water means you are adding some acid in water. Acidulated water you add, again you can see the current passes. Current passes. Now accordingly tell me, who can conduct electricity here? Salt solution, copper sulfate solution, acidulated water. That means who are they? Are they electrolytes or non-electrolytes? Electrolytes. They can conduct electricity. Why? They have mobile ions. They have mobile ions. And they fall under ionic compound. Salt solution, sodium chloride is ionic. Copper sulfate, ionic. Acidulated water means you are adding an acid into water. Okay, acids and bases are also falling under electrolyte percent. So these are electrolytes. And what about this distilled water and kerosene oil? Oh, sugar solution also okay? Same thing. Sugar solution also cannot conduct electricity. Okay, they don't give deflection because they have no mobile ions since they are non-electrolytes. Since they are non-electrolytes. You understand that point? Okay, so accordingly, you see ionic compounds, acids, bases, okay, ionic compounds in molten state, not solid state. Solid state, they can't conduct electricity. Okay, you take salt powder, you dip this setup into salt powder container, there won't be current passing. There won't be current passing. But the same thing, salt powder dissolved in water, you put it inside, then there will be a current pass. You understand my point? Solid sodium chloride container you take and you dip these two graphite rods inside, current will not pass. To make it easier, let's say I'm connecting a bulb will not light. But the same setup, you dip it inside salt solution or molten salt, that means melting, where you are melting into liquid salt, or else dissolving in water, aqueous salt. Now you can see the bulb will be lighting. Bulb will be lighting. So it shows you that ionic compounds in liquid or solution state can conduct electricity. They are the electrolytes. They are the electrolytes. Covalent compounds, even in liquid O solution state, they can't conduct electricity. Can you tell me the reason now? What is the reason? What is the reason? What they do have? They don't have mobile ions. Freely moving ions are not present. What about them? They have mobile ions. That's the reason. Did you understand the point? Is that clear? Now this setup when we are doing one by one at once we can't put, right? Let's say you put some distilled water. So distilled water is fine. You are putting some kerosene in. Okay, you are checking up with the setup process, and then you are going to replace it with salt solution. You can't just straight away put salt solution because already kerosene oil, even you take it out, small drops may be there in it. So you have to wash it with distilled water. After that one, you have to put salt solution. Now you may ask me that distilled water will be there. It doesn't. It doesn't pose a problem because distilled water means only H2O molecules. And the H2O molecules are already there in the solutions. Okay. And anyhow, they can't conduct electricity. So they want to pose a problem. And in between every setup, you have to wash the container. Container means inside and not the outside. Okay. Inside, you have to wash it up with distilled water. Fine. Now, what about drinking water? If you apply drinking water, what happens? A small current will be passing. Then what's the difference? Distilled water means, guys, remember, only water molecules present. No any other things added over. Then what about the drinking water? Is it only H2O? We say H2O. Is it only H2O? No. Drinking water is not a compound, remember. Can you remember? Pure substances we divide elements and compounds. Non-pure substances homogeneous and heterogeneous. Distilled water is a pure substance. It is a compound. It contains only H2O. Drinking water is not a pure substance. That is not the literal meaning pure, clean, not that meaning, okay? I'm not saying it is not clean. Literal meaning is clean. Under chemical composition, it is not a pure substance. It is a non-pure substance. Why? It contains H2O, ions, minerals, salts, respiratory gases, microorganisms may also be there. So, chlorine added means chlorine is there. So a lot of substances are there in the drinking water we consume. So this is not a compound. It is a mixture. What type of mixture it is? Homogeneous mixture. Can you see anything inside? You can't see anything. No, it seems to be like totally water, right? So it is a homogeneous mixture. So remember, distilled water is a compound. It is an electrolyte. Drinking water is a mixture and it may pass a small amount of current. That is why with hands you touch the current, you will dance, right? Right? Current passes. Current passes. Small current would be passing. Sudden shock would be there. Suddenly you will be taking your hands away, right? At least up here, sometimes you will be getting the current shock, right? Okay. Why? It can conduct electricity. And that is why we say with the hands, don't tackle them, don't, do operate with these electric devices. Clear the points now? Okay, I have explained all completely here. Okay, fine. So accordingly, that is what given over there in that setup. Go to the next page. So we have something to write. What is that? Liquids or solutions causing deflection in the ammeter. So tell me which ones cause deflection? Which ones are causing deflection? Out of these five, who are causing deflection? Salt solution, copper sulfate solution, acidated water. Write them here. 1, 2, 3. 1, 2, 3. Write them. Causing a deflection and do not cause a deflection. Not causing a deflection, kerosene oil, distilled water. Okay, so let's write that down here accordingly. The liquids or solution, let's write accordingly. Liquids or solutions which contain mobile ions. Contain mobile ions. Which contain mobile ions can conduct electricity. Can conduct electricity, and they are called electrolytes. And they are called electrolytes. And they are called electrolytes. So let's try the next one accordingly. Liquids or solutions liquids or solutions which do not contain mobile ions. Which do not contain mobile ions. Which do not contain mobile ions. Cannot conduct electricity, and they are called non-electrolytes. And they are called non-electrolytes. Okay. Fine. Positive electrodes and negative electrodes. Positive electrodes and negative electrodes. Okay. Now, what is this positive electrode and negative electrode? There are some names we have to learn. Some terms are there. When you come from electrolytic cell, what is this? Electrolytic cell. This is called electrolytic cell. Okay. Electrolytic cell. So, in an electrolytic cell, there are some parts you must know. That is, the liquid or the solution we are using is called electrolyte. Okay, the liquid or the solution we are using it is called as the electrolyte, and that is what can conduct electricity. Okay, and this is the electric supply, the power supply. There is an external electric supply. Okay. And there are two graphite rods. One is connected at the positive terminal. Can you see? This is the long terminal, right? This is the long terminal, and this is the short terminal. Okay. One is connected to the positive terminal, you can see, and this is called positive electrode. Positive electrode. Another word we are giving anode. What is the word? Anode. The electrode, which is correct. These are the two electrodes. Okay, graphite electrode there. What is the material we are using? Graphite. Carbon, graphite. Carbon, graphite. Okay. Or else platinum we can use. Carbon or graphite or platinum we are using. Now the electrode which is connected to the positive terminal also becomes positive. Also becomes positive. So it is the positive electrode, or else we name it as the anode. So the same way, the electrode which is connected to the negative terminal of the electric supply. So we name it as negative electrode. What electrode? Negative electrode. Or else another word we are giving cathode. What is the word? Cathode. So anode is the positive electrode, cathode is the negative electrode. Anode is the positive electrode, cathode is the negative electrode. Negative electrode. You understand the point? So anode was positive electrode, cathode negative electrode. So these are the terms that we must know, and these are the connecting wires. So what is this? This is the connecting wires. Connecting wires. So it's totally the connecting wires. Did you understand the setup? Okay. So shall we write the positive electrode? The electrode, quickly write, okay? The electrode connected to the positive terminal, connected to the positive terminal, connected to the positive terminal of external electric supply, connected to the positive terminal of external electric supply, positive terminal of external electric supply. Called the positive electrode. It's called the positive electrode. External electric supply is called the positive electrode. Positive electrode. The other side, right? The next one, negative electrode. The electrode that is connected to the electrode that is connected to the electrode that is connected to the negative terminal of the external electric supply. External electric supply is called the negative electrode or cathode. Negative electrode or cathode. Okay. Shall I label them? The diagram is already given below the parts. Quickly label them. And remember the terms, okay? How to label them, you have to remember. Right. Now we said the electric energy will be converted into chemical energy, right? So there will be a chemical change given. Chemical change will be given. How do we actually find out if there is a chemical change given or not? No, we are learning that there will be a chemical change given. These things will be happening. Electric current will be passing. So and so we are speaking about. How do you observe that? What are the witnesses? What are the evidences? The evidences that we give. Okay. There may be a gas liberating off. We can see somewhere here a gas bubble would be moving. Some gas bubbles will be moving on. Sometimes a color change will be given in the solution. Right? Or is a light, a sparkle, or is a firing will be given. A sound will be given. or something will be deposited. Over there, here, over the bottom of the container, there will be some substances deposited. Okay. Or temperature will be increasing or decreasing. So if any of these changes are happening, then we have to say that yes, there is a chemical change. So if there is a chemical change happened, only then one of these observation or some of these observations will be given. So at least one of the observation could be seen in a setup like this, shows that there is a chemical change happening. So such changes are what we term as chemical reactions. What reactions? Chemical reactions. So chemical changes means chemical reaction. Chemical reactions. Do you understand that? Okay. So there will be some of the changes happening. What are they? Have a look on the tube. You can see there. During electrolysis, various chemical changes occur in the substances applied in the system, such as what are they? Liberation of gas, liberation flowing out of a gas, precipitation. Actually, the color should come there down. Okay, it's given at the same line. You can just write it as a separate topic, separate point. Okay. Precipitation means there's something depositing down. A substance depositing down is called precipitation. What is precipitation? Anything depositing down. Okay. Color change. Color changes. Dark to pale. It is changing or a different color would be given. Heat change. Temperature changes, increasing or decreasing. Odor change. The smell changes. Smell changes. So these are some examples. Okay. So some of the activities to determine this electrolytic processes we are going to take. We are going to take. What is the first one? Actually, that is about copper sulfate. That is about copper sulfate. So let's have a look now. This is the setup. Okay. This is the setup. I want you to quickly read what is given there. Just 2 or 3 lines given on your tube. Quickly read that, please. Yeah. Okay. What are we doing here? What are we doing here? Now you can see we do have a container. What do we apply here? A liquid or a solution which can conduct electricity. Give me one word for that. Quickly tell me. A liquid or a solution that can conduct electricity. One word. Electrolyte. One electrolyte I am going to apply. Now my topic is copper sulfate solution. Right? I am going to electrolyze by copper sulfate solution. So copper sulfate solution is what I am using as the electrolyte. Electrolyte is copper sulfate. Carbon electrodes. Remember, under electrolytic cells, what are the rods we are using? Always carbon rods or else platinum rods. Carbon, or we say the form of carbon is actually graphite. Graphite rods or else platinum rods we can use. No any other metal rods we are using here strictly. Okay. Now, it is a positive terminal. You can see the positive terminal is there and the negative terminal is there. So, to the positive terminal is connected will be the positive anode. Negative terminal is connected will be the negative anode. Correct? Correct. So can you see the setup here? You have an ammeter and it is connected over there to this electrode. Tell me what is this electrode? How do we name this electrode? Is it positive electrode or negative electrode? Negative electrode. Give me one word for that. Anode or cathode? Cathode. Cathode. Negative electrode is called cathode. How do we name this setup? Positive electrode, anode. Right. Now, whom I have here? The solution is CuSO4, AQ. AQ refers to aqueous solution. What I can observe, it is the positive electrode. Okay, this is the positive electrode, right? And this is the negative electrode. Okay. I can see some changes. Actually, three changes I can see. I can see three changes. So, what are the three changes I can see? First, before the changes, can you tell me again? Tell me again. Who is this positive electrode? How do you name the positive electrode? Anode. How do you name the positive electrode? Anode. How do you name the negative electrode? Cathode. Right. Now, we can see here, positive and negative electrodes are there. I can observe at the negative electrode, reddish substance is getting deposited. I can see some reddish substance getting deposited here. But I can see a reddish substance is getting deposited. So one observation. I told you earlier, you can remember precipitation, something will be deposited now. What is the something? Actually here, copper deposits. What is depositing here? Copper. Copper deposits here. So at the negative electrode, I can observe a reddish substance deposits. And can you see it is only below the layer? Why? Below the layer only the chemical change is happening, right? Above the layer, there is no current passing. I mean, no current passing across the liquid, right? There is no liquid contact, correct? Can you see? Above this line, there is no liquid, no? So liquid contacting, we can't take there. At the positive electrode, I can see there will be a gas liberating. There will be a gas liberating. A gas moves out. A gas will be bubbling out, I can see. Gas will be bubbling out. Gas bubbles are moving up, I can see. That is the second observation. And the third observation, copper sulfate is usually dark blue color. Okay, very blue color. Now you can see this blue color reduces. Blue color reduces. So how many changes are happening? Three changes. What are the three changes? At the negative electrode, a reddish substance deposits. On the negative electrode, a reddish brown substance deposits. Or even down there. That is copper. Second one, at the positive electrode, a gas bubble moves out. Gas bubbles are moving. Gas bubbles are liberating out. Third one, the blue color of the electrolyte is electrolyte, copper sulfate. The blue color of the copper sulfate solution, the blue color of the electrolyte slowly reduces. So these are the three observations. Did you understand that? Clear? Shall I write there? Look at the observations in electrolyte. Let's write there. The blue color of the solution, gradually reduces. The blue color of the solution gradually reduces. Blue color of the solution gradually reduces. Second one, at the positive electrode. Liberation of gas bubbles can be observed. Liberation of gas bubbles can be observed. At the negative electrode, deposition of a reddish brown substance. Can be seen. The deposition of reddish brown substance can be seen. Deposition of a reddish brown substance can be seen. Okay. Right, done. Fine. So what are the three observations again? Tell me. Now these three observations you have to memorize. Okay, that comes in the questions. In copper sulfate solution, electrolysis of copper sulfate solution. Whom we use as the electrolyte? Copper sulfate. Tell me whom we use as the electrolyte? Copper sulfate. Whom we use as the electrode? Carbon rods. Carbon or else graphite rods. Or platinum rods we are using. What is the observation in electrolyte? Electrolyte observation. Color reduces. Blue color reduces gradually. Observation at the negative electrode. Reddish brown substance deposits. Observation at the positive electrode. Gas bubbles liberate up. You understand that points? Clear the way? Fine. Okay. So we wrote that right. So accordingly, read them. During this process, copper sulfate undergoing the chemical change has turned into copper, a simple substance. Can you see that? Now this is copper sulfate, right? What is deposited there? Copper. What is deposited there? Copper. Is that correct? But we said earlier, electrolysis means breaking larger complex substance into smaller substances. Okay. So from copper sulfate, copper you have taken out. Copper you have taken out. So this is electrolysis. This is electrolysis. Underline that. And also whom we are using as the electrodes here, a substance which is not chemically reacting with others. Madhi, whom are we using as electrodes here? A substance which will not chemically react with others. There won't be chemical reactions with others. They are inert, we say, but not inert. INERT. Inert means they don't chemically react with others. They won't chemically react with others. Okay, read there. Do you know a substance that doesn't react chemically with the electrolyte referred to as inert electrodes? Underline. Inert electrodes. Right? Carbon and platinum electrodes are such examples. Underline carbon and platinum. Carbon and platinum. Fine. So I wanted to go to the writing book. Okay. These setups are already there on your tube, but one diagram we have to draw again anyhow because it's wrong. Actually, wrong means it's placed. So I want to draw this quickly on your writing book. Yes. Take the topic. Electrolysis of copper sulfate solution, and I want you to draw like this. Use a pencil to draw and mark this in red color. Gas bubbles you have to show. Gas bubbles you have to show. Okay. Mark it down quickly. Once you are done with that, I want you to do this. Okay, you have to draw this because anyhow this diagram is wrong on your tube. It is misplaced. A different diagram is good, so I want you to draw this as well. After you are done with this, okay? After you are done with this, you have to draw this. This one's topic, electrolysis of copper sulfate solution. Electrolysis of copper sulfate solution. Once you are done with this, you have to draw this part, okay? You have to take the topic acidulated water electrolysis. Electrolysis of acidulated water. This one, electrolysis of copper sulfate solution. So this the topic is electrolysis of copper sulfate solution. And after that, we have to do this. Okay? Let's mark it down quickly. Electron is widely applied in three areas to one of the features that are applied in major applying to OR is done. It is also also so it's not because that's not you are using a request of Can you see? Right. Now look at this setup. We are done with this part. Electrolysis of acidulated water. Okay. So what is acidulated water? We take some water and some acid, we are going to mix it. Maybe HCl acid, sulfuric acid. Okay, better we take sulfuric acid. So sulfuric acid means H2SO4. What is sulfuric acid? H2SO4. We are going to mix. We are going to mix. Now such a mixture is what we are taking as acidulated water. Now you see the setup is a bit different. Okay, setup is a bit different because in the previous setup, guys, we gonna collect some sort of observations where a substance is deposited. Okay, but here gases are to be released and we are going to collect the gases. Earlier we didn't collect the gas. Now here we are going to collect the gas. How to do this? How to do this? Okay, now I have the rods down here and you see these are the two rods I have. These are the two rods I have. And both the rods are connected over here as plus and minus. As plus and minus. Both rods are connected as plus and minus. So you see here, it is 9 watt battery. Actually, it is given as one dry cell, but it is not one dry cell. Set of dry cells are there. 9 voltage battery it is. Tell me, to give 9 volt battery, how many dry cells should be connected? You have an idea? 3, 6. Why is that? How much is one dry cell? 1.5. Then how many 1.5s are needed? 6, right? How many 1.5s are needed? 6. So 6 dry cells are needed. So we can't draw all 6, right? So that we are just drawing one. Okay. Now, this is my positive terminal. This is the negative terminal. So the positive electron, negative electron are there. Now you see, both the setups are covered by 2 inverted tubes, and this is totally acidulated water. Acidulated water. So here, you see here, this container, it's a tube down, and there's another tube. Okay. Actually, earlier it's totally filled up with water. It was fully filled up with water. Okay, fully filled up. Even here it was fully filled up with water. What I can observe, once the current is passing, once the current is allowed to pass. Now, electrolysis means electric energy is getting converted to chemical energy. A chemical change will be given, right? What is the chemical change? I can observe gases are evolving from both the electrodes. From the positive electrode also, closer to positive electrode also, there is a gas evolving. Negative electrode also, there is a gas evolving. And here the gas is collected somewhere closer to this level. And here the gas is collected somewhere closer to this level. So, two types of gases are collected. Two types of gases are collected. At the positive electrode, we collect oxygen gas. And then negative electrode, we get hydrogen gas. What are the two gases? At the positive electrode, oxygen gas. At the negative electrode, hydrogen gas. How and why? It is not here now. It is in grade 10 level. In actual grade level. Here we learn only the observations. Because we need chemical equations, which we haven't learned, which we are not supposed to learn in. Okay. So we just name by oxygen and hydrogen. So oxygen gas is collected at the positive terminal, negative terminal, and the negative electrode, we get hydrogen gas. So first observation is gases evolve at both the ends. Positive electrode it is oxygen, negative electrode it is hydrogen. That is the first observation. What is the second observation? There is another observation. What is that? Look at the level of the gas. It is a small amount. This is almost double the amount, isn't it? How much oxygen is there? Like that, almost double the amount of hydrogen is there. Correct? Double the amount of hydrogen is there. So this is the second observation. What is the second observation? Volume of hydrogen gas collected is twice as the volume of oxygen gas. Volume of hydrogen gas collected is twice as the volume of oxygen gas. Oxygen Yes, understand? So volume of hydrogen gas collected is as twice as the volume of oxygen gas. Oxygen gas. Now you see, this is second observation. Okay, second observation. So the question will be asking you, what are the observations at the positive electrode, negative electrode? Okay. Who is more? Is it hydrogen or oxygen? These are what the question asks. That's it. So this is the product of acidulated water electrolysis. Why? H2O plus an acid. This is what acidulated water is. What is it divided into? Can you see H2 separately, O2 separately are taken. For complex compound or else a larger component is broken into simpler components. Simpler components. So this is what our motive of electrolysis. Correct? By electrolysis, what we expect is this, right? Larger complex compounds are broken into smaller simple components. So accordingly, electrolysis is done here. Did you understand the setup? Okay. So what are you supposed to remember? Positive electrode, oxygen gas is collected, and the negative electrode, hydrogen gas is collected. Second observation, hydrogen gas collected is almost twice as the amount of oxygen gas collected. Oxygen gas collected. Clear the point? Okay. So shall we write there? Observations. At positive electrode, we write. At positive electrode. Yeah. Yeah. Go to the tube. Go to the tube. And on your tube, can you please cut this by one line? Cut this by one line and mark the refer to notebook. Refer to the notebook. Under that acidulated water, it's a wrong diagram, right? Same diagram is repeated now. Cut that diagram. Yeah, that diagram, cut it. Cut it by one line. Again, just write there down, refer to the notebook. Refer to the notebook, okay? Let's write down. At positive electrode, right? Oxygen gas, O2 gas evolves, O2 gas evolves, EVOLVES evolves at the positive electrode. Oxygen gas evolves at the positive electrode. At the positive electrode, at the positive electrode. Next one. Hydrogen gas, H2 gas evolves at the negative electrode. H2 gas evolves at the negative electrode. H2 gas evolves at the negative electrode. Remember, positive electrode, oxygen gas, negative electrode, hydrogen gas. Hydrogen gas. One more point is there. Read. In this activity, it can be observed that the gas bubbles evolve at the electrodes. The gases evolved get collected in the test tubes. Underline from there. The volume of the gas collected at the negative electrode is approximately twice the volume of the gas collected at the positive electrode. Correct, right? At the negative electrode, what is the gas collected? Is almost 2 times like the gas collected at the positive electrode. Correct? Correct? Hydrogen gas collected is as twice as the volume of oxygen gas collected. That is the idea. Underline. And then within bracket right there. Within bracket right there. That we write. Within bracket. The volume of hydrogen gas. The volume of hydrogen gas. The volume of hydrogen gas collected is. The volume of hydrogen gas collected is as twice as the volume of oxygen gas collected. Oxygen gas collected. Okay. So you read there. What is the next page? What does the next page say? Read. How do you identify the evolved gases as oxygen and hydrogen? Now, how do we find out if the gas is hydrogen or oxygen? Now, the gas collector is there. Now, this gas collector, it is in the tube, right? We are waiting until a large volume of gas is getting collected. Okay. So, it is the gas here. Okay. Now, what I do? I'm going to take a glowing splinter. What splinter? Glowing splinter. Like an elabor. No? Elabor you have seen. Everywhere it is glowing up. So, the glowing splinter. Don't use an elabor here, okay? Because it's a cracker, right? Okay. So, the glowing splinter we take, the gas is there over. Now, if the gas is oxygen, if the gas is oxygen, you know what happens? The glowing splinter, it will be reigniting, it would be, burning again, giving a bright flame. It burns again, giving a bright flame. If it is hydrogen, you know what happens? Same setup, but different observations. If the gas is oxygen, it burns again, giving a bright flame. So we can know, we can understand that is oxygen. Next if it is hydrogen, it burns with a pop sound, a spiky sound, a pop sound would be. A pop sound given means then you have to understand that that is not oxygen, that is hydrogen. Let's say this carbon dioxide. Let's say it is carbon dioxide. Carbon dioxide is not there in this activity. Let me anyhow write it. Because these are the common activities for all three gases that we do. If it is carbon dioxide, you know what happens? The fire, the glow goes off. Why? Carbon dioxide is a non-support of combustion. And that is why a candle flame you blow out here. Would it be burning again? No, right? It is not a fuel you are applying, right? It goes off, correct? A matchstick light, you blow, it goes off. Why? Because it is an unsupportive combustion. What is the gas we are evolving at releasing? Oh, carbon dioxide. Carbon dioxide. Do you understand that? Clear the point? Right? Fine. So you already give the diagram, right? Previous diagram you drew, right? Below that we write them. Below that, right? How to determine? How to determine? What write it go? When you drew the diagram. How to determine the gas collector? How to determine the gas collector? Okay. Now you can write, okay? You can write, take a piece of paper. How to determine the gas collector? Right there. When a glowing splinter is subjected, when a glowing splinter is subjected, when a glowing splinter is subjected to the gas jar, to the gas jar, to the gas jar with take the first point oxygen and a small semicolon or double or whatever, just write there front oxygen, write oxygen and then write there. It burns again, giving a bright flame. Burns again, giving a bright flame. Burns again, giving a bright flame. Right? bright flame. It burns again, giving a bright flame. Second one, hydrogen. Hydrogen. And right there. It burns, giving a pop sound. It burns, giving a pop sound. It burns, giving a pop sound. Third one, carbon dioxide. It glows O. It glows O. And just draw this close by. It glows O. For carbon dioxide, it glows O. Glows O. That means it's going O. Running O. It glows O. Okay. So accordingly, where do we use these electrolysis? Applications of electrolysis. Where? Use this electrolysis for extraction of various metals. Read that. Extraction of various metals. Extracting means from the way they are found in the environment, as a mixture they are found, from that collective mixture, only the needed metal we take out. We can't just take it over physically because they are chemically combined. Chemically combined. For example, sodium chloride. We need sodium, but sodium is chemically combined with chlorine. So to take this sodium out, we have to apply chemical methods. Electrolysis we are using. Likewise, many metals are there in this way from their metal ores. Metal ore means how they are found as a compound in the environment. Okay, what is the form? They are found in the environment as a compound. So from this metal ore, what is the method we use to separate them out? Mostly electrolysis. Next one, industrial manufacture of caustic soda, sodium hydroxide and many other substances to be produced industrially for economical benefits. They are also we are using electrolysis. And then electroplating. Electroplating also we need electrolysis. We need electrolysis. Is that clear? For electrolysis, electroplating also we need electrolysis. Right? So did you understand totally about this electrolysis part? Totally about the electrolysis. Is there any questions? You have to refer them, okay? Only one more part we have electroplating. With that, we are ending up the lesson today. And then 11th chapter will be taken at the next class. Okay, we'll have a short break, just 5 minutes, and then we'll continue with the electroplating part. Clear? Fine. If you want to drink water, finish up and come.
Also, the kinship with three examples again. So, to consider statement, the question you want to hear about the last minute. The areas of fiction and the marks. It's outside the next year. We can have it's I have to be as one of the maybe I think it's they have an eyes and it's for the set. Because of that fiction for strong was example. My reason how now see now the throne and something in the throne event. But there's some throne example of daily use. Other second subject was strong. That's not the but one thing is they are now question of media making any structure of anything else. Certain aspect kinship provide an example for instance at least take this week. Administrative history. They using it for exactly the past and everything, but sometimes it's not. This is very hard to do for this bits. I'm not saying about the same guys that see it. This is here. This is some existence. But I have just learned it's separation. It's very hard to say. Service, they are okay. I would say that I'm specific. Office in charge of round Scix. At least I would say he does like trust her. If you can see the work, because it's not I get up as a say I love it. If it was I didn't think myself a said. I think of just first to grab up my explain the contribution that's right. One for the family with the 6 8
Fine. You had a good break, right? So let's head up with the last part now. Electroplating. Electroplating. So what is this electroplating? Electrolysis we learn bringing about a chemical change by passing a current. So electric energy is converted into chemical energy, right? Now this change we are applying in order to plate a metal on another metal surface. Plate a metal on another metal surface. Now metal we can't paint, right? I mean paints you can paint, okay? Over the metals or whatever you can paint. A metal as a liquid you can't paint on another, right? Right? Or you can't paste it over there. So there are some occasions where we have to give one metallic nature onto another metallic surface. How do we do that? Using current. Using current. For example, we say the best example is imitation jewelry. You are saying, no? Loads of golds you are applying, right? But when you scratch and see only, you know if it is real gold or not. No? Say tangama, takarama, you know, no? Only then, fine. So yes, it seems to be like gold. Seems to be like gold. It's all gold plated sometimes. So what is this plated? Using current, we plate one metal over the surface of another metal. Another metal. So this is what we term as electroplating. Electroplating, electrolysis process is what we are using here. So let's write there. The plating of a certain metal the plating of a certain metal on another metal surface. Quick right. Plating of a certain metal on another metal surface using electricity. Using electricity is referred to as electroplating. Is referred to as electroplating. Okay. Fine. Right? Start writing. Hurry up, please. And we go to the next part. We have to fill up some points. There are three terms given: electrolyte, positive electrode, and negative electrode. Electrolyte. Shall I write? Hurry up. Front of electrolyte we write. Front of electrolyte. The solution of salt. The solution of salt of the metal the solution of the salt of metal that should be plated. That should be plated. That should be plated. And then we write the positive electrode. Whom are we using as the positive electrode? We are using, let's write there. The metal that needs to be plated. The metal that needs to be plated. The metal that needs to be plated. Okay? The metal that needs to be plated. And then we write for the negative electrode, the object that is plated with the metal. The object that is plated with the metal. The object that is plated with the metal. Okay? Right? Fine. So guys, you see, what do we use here? We do have a setup. Where we are having a positive electrode, negative electrode, and the electrolyte. Electrolyte is a solution which can conduct electricity, right? It is a solution which can conduct electricity. Now, there we use the metal solvent. Okay. Now, it's something like this. What's wrong? Let's say it is the cell we are using for electroplating. It is external supply. Okay. And this is the ring or any sort of circular metal, circular surface that we have. Now look at this. It is the positive terminal. This should be the positive electrode, correct? This is the positive electrode, right? And this is the negative terminal. So this has to be the negative electrode, correct? Negative electrode. Okay. Now you see whom we use. Look at this. We wrote earlier. Can you read what is given at the metal? What is given at the positive electrode? What we wrote? At the positive electrode, right? The metal. What is it? The metal that should be plated. So you see, the metal that should be plated is what we use at the positive electrode. Okay, the metal that should be plated, we are using it at the positive electrode. Right? What is the negative electrode? The object that is plated with the metal. The object that is plated with the metal. For example, let's say you want to plate gold on yakada. Now, imitating yakada with gold on, right? You are going to plate gold on iron. An iron ring you are having an iron ring. You want to plate gold. So the iron ring is the surface you want to get plated, right? So that iron ring should be used at the negative side. Negative side. Iron ring, whom you want to get plated with? Gold ring. A gold biscuit, a gold metal rod you have to use at the positive electrode. The metal that should be plated. Gold is the metal you have to plate. Where you want to plate? On the iron ring. Iron ring should be the negative. So what you want to plate should be plus, should be the positive electrode. Where you want to get it plated should be the negative. Got it? What is the metal you want to plate should be the positive electrode. Where you want to get it plated should be the negative electrode. Should be the negative electrode. Right? And the electrolyte. Who should be the electrolyte? Electrolyte should be salt of the metal here. Salt of the metal plated. Salt of the metal plate. And what is the metal we are using? That metal containing salt we have to use here. The metal containing salt we have to use here. You understand that? So for an example, gold means gold salt. Silver means silver salt. Anything, any sort of chemical compound containing that metal we have to use. You understand that? Right. Now according, let's say you want to plate iron with iron ring or iron bracelet or something, you want to plate with silver, then iron object you have to use as the negative electrode. Silver rod you have to use as the positive electrode. Silver containing salt you have to use as the electrolyte. You understand that point? Clear? So what is the object you want to plate? What is the metal you want to plate? Should be positive. Where do you want to plate that metal? The surface, it should be the negative. Metal plating, the plating metal containing salt should be the electrolyte. You understand the points? Clear the points? Okay, so shall I mark it down? Go to your notebook. Go to your notebook, please. Take it as electroplating and mark it down quickly. Take the topic electroplating. Quickly write it down. Right? Hurry up, please. Hurry up. Yeah, there's a question. Listen, can you plate gold with any other metal? Just like this. So usually you're plating a lower reactive metal on a high reactive. Okay. In that case, according to the reactivity series that we are learning, actually you will be learning in grade 10. Okay. In that part, we have gold at last. We have gold at last. So gold is not being used to plate on others. No other materials usually are used to plate on gold. Is that clear? Fine. Now, why actually we need this plating? We need this plating because we need to use different materials. We might be having just yakada, iron. We need to give a lustrous surface for this iron, a shiny surface for this iron, an expensive look, a rich look for this iron. So what we do, we plate gold, we plate silver, okay, we plate nickel, sorry, we plate platinum, right? So like some shiny surfaces we are going to plate. So by doing so, we get a rich look. Okay, and also we make it corrosion resistive. Resistant for corrosion we make. Resistant for corrosion we are making. So accordingly, you see, these are some features. These are some purposes of doing this electroplating. Fine. So there's a small part given as an activity. Could you please read that quickly? Make it fast. We have to finish it up. Read what is given there. What does it say? You have this setup. Okay. In this setup, whom you want to get plated with? Can you see? You have copper, correct? Whom you are having? Copper. Take it slightly away. Can you see this? Whom you have? You have copper here. Okay. Copper sulfate. The solution is copper sulfate. Then copper sulfate solution means copper should be the plate, correct? Why? Copper containing solution means copper should be the electroplating metal here. Okay. So this metal is what we are going to plate on an iron nail. So we have a Yakada nail and iron nail, we are going to put it as the negative electrode. And as the positive electrode, we are going to apply a copper plate. What would happen? This copper would be dissolving in the solution, and because of the current passing, along with the ions, this copper moves. Copper moves as copper 2 plus ion. Copper moves as copper 2 plus ions and will be deposited over here. Can you remember a reddish brown substance earlier deposited? Earlier the reddish brown substance deposited. Likewise, copper grows on and will be depositing over this iron nail. And if you are giving a standard plating here, at last you'll be getting completely copper plated iron nail with no any short errors. Okay, totally copper plated. Totally copper plated we will obtain. So that is the observation we can have at last. A reddish brown substance, copper substance will be totally deposited over the iron nail. Now to increase this, to improve this quality, what we do? We have to use a diluted solution, more water added solution. And we have to pass a small current. Now when we are doing a work faster, it won't be very much nice, right? When you are writing fast. But when you are writing slow, nicely you are taking the letters, right? Fine. Likewise, when a small current is passed, the work would be effective. A good quality electroplating would be done. Okay, electroplating would be done with a high quality. And how do you make a high quality or good quality electroplating? By passing a small current and by using a diluted solution. By using a diluted solution, we are making a high quality or high standard electroplating. Okay, so let's read them. We can see what is given over that we have discussed. Below the activity, please have a look quickly. In the activity, it could be observed that the copper plate gradually dissolves and copper is deposited on the iron plate. Underline. What would happen? Here I told you, as copper 2 plus it moves out. So this copper plate will be dissolving part by part it dissolves, we can see the size of this copper plate reduce. Okay, the size of the copper plate will be reducing because part by part it is removing, dissolving in the solution, come to the solution. And that which comes to the solution goes toward the iron nail and will be deposited. So what are the two observations? Copper dissolves from this copper rod to the solution, and the second one, that copper will be deposited on the iron nail. Underline that. It could be observed that the copper plate gradually dissolves and copper is deposited on the iron nail. Here, when the iron nail used in the above activity is taken into a hand and touched its plating with fingers, it could be observed that the copper plating will get removed from the nail and comes to fingertips. This shows that the plating occurred in this way is not in good quality. Now, if it is not in a good quality, what happens? After the plating, you take it and you touch it with your fingers. Over the fingers, gold can be seen, or else copper can be seen. Means it is not of a good quality one. How do you make it at a good quality one? Right? Characteristics of a high quality electroplating. What are the features of high quality electroplating? Number one, coating should firmly adhere to the surface of the electroplating. That means when you keep your hands over, if you touch over there, it should not be removing out. It should not be removing out, it should not be coming off, it should be adhering to the surface. So tightly it has to be plated. You can't remove it out. You understand that? Just because of you keep your fingers, it should not be coming off. Second one, the coating should be of confirmed thickness. It should be having a thick layer. So again you have to do it so that it becomes a thick layer. And then the third one, the coating should be shiny. It should be a shiny surface. It should be a shiny surface. So what are the three? Can you please read? What are the three? First one, coating should be should firmly adhere to the surface. Yes. Second one should be of confirmed thickness, a thick layer. Third one, shiny. Should be shiny. How do you do that? So high quality plating occurs when the electrochemical change takes place very slowly. If you are doing the change slowly, the efficiency would be high. Okay, the output standard would be high. How do you make it? Electrolyte salt solution used for this has to be very dilute. I told you a very dilute solution you have to use. And also, what is the next one? Passing a very low current through the solution, this can be affected by giving a low potential voltage. Okay, draw a box around both those points. Draw a box and highlight. High quality plating occurs when the electrochemical change takes place very slowly. Highlight that and draw a box around. Yes, those two. There's 2 points. 2 points. What we just read. Down on 2 points. You have got highlight. You have draw a box. Now, if we are doing this under controlled condition to maintain the standard, the product would be, the output would be with high standards. Now, what are the examples where we use these electroplating applications? Very often, the lust of the objects such as vases, trays, cutlery, and door locks. Could have seen gold door locks are there. Is that real gold? Huh? If it is real gold, that should be a multi-million, isn't it? Why? Even for the gold, even for the door lock, they are using gold. So that is just imitate gold locks are there. And silver bathwares are there. Bathware sink is also silver. Right? Is it real silver? Cutlery, cookery, the kitchen, whatever you are using, all seems to be like silver. Is it real silver? Plated. All plated. So you see bathwares, kitchenwares, the cutlery, cookery, and all these we are using the trays, vases, door locks. Okay, so hinges, the padlocks, mostly all those particles. So all of them are like plated. And in order to prevent rusting of the parts of motor vehicles, they are coated with a thin metallic layer of electroplating. Now, iron-made objects are there, right? Iron buckets, iron stuffs are there, right? Iron tubes are there, and also iron is being used. Yakada is being used in motor vehicles. So these motor vehicles are always outside, right? Could be exposed to this air and water, can be rusted. If it is rusted, it could be broken. So it's hard to replace. Or else, cost would be, the damage cost would be, repairing cost would be high. So, what are we supposed to do? We should be plating it. How we plate? We plate it to avoid rusting. We are plating these iron-made objects, the lower parts of these vehicles, the motor spares, okay, with high reactive metals. So it will be protecting iron from rusting. It will be protecting iron from rusting. Iron will not corrode. Yakada malagada bendene naha. Right? Why? Because it is corroded. It is covered with highly active metals. So this is also electroplating. What else? Look at this one. Mostly metals like copper, silver, gold, nickel, and chromium are plated like this. Unlike that. So mostly these are the metals we are plating. These are the metals we are plating. What are the metals? Gold, silver, copper, nickel, chromium. In such instances, the metal has a certain property which is lacking in the metal which is subjected to plating, resistance to corrosion, attractive color, luster, good furnish. Now, why actually we need this plating? A good lustrous surface we expect. Shiny surface. Attracting color. Rich look. Seems to be expensive. Okay. And resistant for corrosion. It won't be corroded. Like the iron made studs I told you. Okay. So it won't be corroded. Right? It won't be corroded. So for these purposes only, we are going for electroplating. Underline that point. Resistance to corrosion, attractive color, luster, and good finish. Some examples: electroplating, nickel metal on iron plate protects it from rusting and also gives an attractive appearance. So iron trays are there. We are plating it with electroplating with nickel. So it gives a lustrous shiny surfaces and also it is corroding. It is protecting from corrosion, rusting. Electroplating copper jewels with gold adds value to it and gives a rich look. Now, copper made jewelries or iron made jewelries are there. We are plating it with electroplating with gold and silver. So it is giving a rich look. Okay, a rich look, expensive look it gives, and also it is it's protecting it from corrosion. So these are the purposes why we are going for electroplating. Do you understand that? So these are the examples coming under electroplating. So accordingly, this is the whole theory about electrolysis and electroplating. So basically, you have to remember the setup that we have learned and the example activities that we discussed. Okay. So under electrolysis, we learned about reminder of it. What is electrolytes? Non-electrolytes we learned. Okay. Electrolytes, they are the liquids or solution which can conduct electricity. They have mobile ions. Non-electrolytes, no mobile ions, so they can't conduct electricity. They are the liquids or solution which cannot conduct electricity. Right. And electrodes, positive and negative electrodes we learned. Electrode is connected to the positive terminal in the electrolyte itself, like a positive electrode or anode, which is connected to the negative electrode, negative terminal. It is called the negative electrode or cathode. And under that, acidulated water, copper sulfate solution, we learn as the electrolysis. Then we came for electroplating. Under electroplating, this setup we learn, an example we learn. Okay, so please refer to the whole lesson, and I want you to complete the exercises before the upcoming Saturday's class. Totally complete the exercise of the answers. Clear the points? Okay, so please do complete the works at home and come up with the answers. Fine. So we're ending up with that. See you then. Good evening. Salam. Ending up. Salam. Salam. Good evening. Salam. Then make sure you are going through the recording, okay? Salam.
Okay, sir.
Okay.